Okay. Okay, everybody. So home stretch, one more session. 3:05, starting 5 minutes late. So welcome back. We're going to have three presentations to close out the conference today. As with the other ones, we'll hold Q&A till afterwards. The panel will be seated there and we'll take any questions you might have. I'm going to start off with the first talk today on our FRP composite tub girders, talking about recent developments and some technical advances. And you've heard a bit about the G-beam today. My word for it is CT girder. G-beam is actually a trademark. I tend to use just the more generic composite tub girder. And this is something that you've heard about a few times today, and some of you have heard me speak about it in the past. I will be covering some older material, but there is some new stuff in here that I find particularly interesting, and I think the bridge engineers in the room will appreciate as well. But I am going to go through, in general, sort of the development, what it is, because there are folks here who are not familiar with the technology. So this first slide just gives us the anatomy of a CT girder bridge. So the rendering there on the upper left shows you they're just beams with a concrete deck on there. And they're composite beams. They're FRP e-glass carbon fiber hybrids. It's got a concrete deck. It's got shear connectors. We see the picture on the bottom. It shows you it's an open tub section. There's nothing special about it in the sense that it's just a beam. It's a direct replacement for a steel or concrete beam. It's a substitute for either one of those simple spans up to 100 feet. The picture on the bottom right is just a photograph of the Hamden Gristmill Bridge, which you've seen a few times today in different photographs. The first one of these such bridges built. Now, it does take us, we use FRP when we're interested in corrosion-free structures, low maintenance, but it does take us beyond that. And you heard Joe talk this morning, talking about environmental product declarations, LCA, looking at composites versus steel and concrete. And he had a statistic up there that's identical to what I have. They are 70% less in weight than steel. And that's not on a density basis. That's on an equivalent beam basis. If you designed a steel girder bridge with a certain spacing and you designed an FRP girder, a CT girder at that same spacing, that FRP girder would weigh 30% of what the steel girder does. But that cross-sectional shape also greatly reduces shipping volume. The rendering on the left shows that. That's been realized. AIT fabricated a number of girders for a 2 or 3 span structure down in Florida. Their shop up here in Brewer, Maine. They were all shipped down there on one truck. The logistics is real too in terms of construction. You can see with the Hamden Gristmill Bridge, we've got 2 CT girders, 75 feet long, being picked with 1 crane. They're attached together with utility hangers. You can see the utilities pre-hung. That was another advantage for the contractor. We would not be lifting a pair of steel, let alone concrete girders with 1 crane. Now, we've done a lot of research on this. This morning in our opening panel, Joyce Taylor made a comment that, we work with the university, but we have to understand that it takes a lot of work. University needs to do long-term, long-reaching things. Our codes are based on research. They're based on fundamentals. And that's our role at the university, is to make sure we really do our job there. It's come up with an idea, but it's incumbent on us to prove that it works. And so we've done a lot of that. And this slide in no way summarizes 5 years worth of research, right? But that's kind of what it took to prove out that the concept worked. And that's everything from doing basic testing of the first prototype, shown up here on the left in 2018, and look at the load displacement response on the right, and you see it going up to failure. And we see that it carried 2.65 times a strength 1 factored load. In other words, practically speaking, there's a factor of safety inherent in this of about 5, which seems unreasonably high, but it's actually perfectly consistent with our design assumptions and the conservatism that we build into this for a variety of reasons. It agrees very well with what we would predict. But we can't just test our way to the answer for everything as well. We have done a lot of very sophisticated modeling. If we look at shear in the webs, we've got to worry about strength. We've got to worry about buckling. We can't afford to do a full bore FEA for every bridge we design. So one of the things that we did here at Maine is run a suite of hundreds of finite element analyses, parametric studies, come up with the buckling capacity of webs for different thicknesses, face sheet thicknesses, foam core thicknesses, and then distill those into design tools like you see on the right that says, oh, I have a certain foam core web thickness, I have a certain face sheet thickness, and here's the height of my web. Oh, there's a buckling capacity, right? That's the kind of thing we need to take this out into practice, to develop a design guide, to use this efficiently, to design this efficiently. And that's the kind of thing that we need to do. Now, in parallel with this, we've been very fortunate. 4 of these bridges have been built to date. 2 of them are quite close to us, both in Hamden, Maine, actually. And that has afforded us the opportunity to do a lot of field live load testing. That's something over my career I've done a lot of. I really enjoy it. I like to get out there with the right people that really know how to run the instrumentation, because trust me, you don't want me in charge of the instrumentation. I'll tell you where to put the sensor, but I'll make sure somebody else is hooking it up and making sure the data is good, right? But it's great to go out there and put 260,000 pounds on a bridge and see how it really behaves. And we need to do that because this is a new type of structure and we're not exactly sure how it's going to behave. Does it agree with our design assumptions? And indeed, it generally does, but there are differences. We need to quantify those and take those into account in the future as we advance our design methodology. That's a picture of our first live load test of the Gristmill Bridge, which was back in very late 2020, New Year's Day. But we have since conducted 3 additional live load tests, both on that bridge and on the other bridge in Hamden. And we've load tested them not just for moment, but also for shear, because those are the 2 main strength limit states we're designing around. So we got a tremendous amount of data out of that, and it's been very, very helpful to us. Now, at this point, we step back, and it's a lot of other stuff we did, but that's 5, 6 years, 7 years worth of research. And we had tested 1 beam to failure in the lab, right? We built 4 bridges, we've tested 1 beam. Now, and a lot has changed since that first beam we tested. That was truly a prototype. It had precast deck panels on there. It had shear connectors that are not what we actually put out in the field today, sort of different fabrics used in the layup, 1 beam. And if you think about the AASHTO specification for designing conventional steel or concrete girders, thousands upon thousands, if not tens of thousands of specimens have been tested to validate and develop those design methods, right? We've tested 1 beam. So we thought it might be good if we tested a few more. And we're very fortunate with this UTC funding and support from the Maine DOT, and a bridge had recently been built down in Rhode Island. We were able to get 2 girders that were nominally identical to the girders used in the bridge in Rhode Island. And we were able to test those in the lab. That occurred over the last year and a half, roughly. One of those are 38-foot spans, 5-foot wide, 8-inch thick deck, very standard construction, but it had all of the current shear connectors in it, had some ply drops in the bottom flange. We instrumented them very heavily, put them in 4-point bending. And because we had 2 beams, that also allowed us to do a full-scale fatigue test. That's another limit state that we had not explored experimentally. We put carbon fiber in the bottom of these girders because carbon fiber is very good in fatigue. That's generally accepted. However, when we talk about carbon fiber being good in fatigue, we're typically referencing aerospace grade composites. This is a big vacuum infused girder. This is not an aerospace grade composite. There are scale effects. We need to quantify those scale effects. So here's our first test. This is the first beam we tested. We did a strength test on it, loaded it to failure, and very similar behavior to what we observed with our first prototype back in 2018. So this happened in early 23, 313 kip failure load. We predicted 317 kips with our model. Very good agreement. Everything looks good. And you notice again, there's our AASHTO factored strength 1 loading is more than 2 times less than the load it failed at. Very consistent with the first test, in line with all of our expectations in terms of design. Then we went on and we said, we're going to fatigue the other one. We're going to subject it to 3 million cycles of a factored AASHTO fatigue 1 loading. And for the bridge engineers in the room, that's a load factor of 1.75 on the fatigue truck. That's actually a very big load. It's not a small load. It is much larger than a typical vehicular load, truck load that would be on the bridge in the real world. And I don't know, how many of you have run fatigue tests before? Yeah. Running them on something 38 feet long is not a lot of fun, okay? The test occurred over a period of 3 months. At the rate we were running it, it should have been done in about 3 weeks, right? So it took 4 times as long as it would if everything worked, because things just don't always work when you're running at this scale, right? You get leaks, you get failures, you get this. You notice a little thing there, test pause for 3 weeks. Well, that's because the fire suppression equipment in the lab went down. We had to shut all the equipment down for 3 weeks. This stuff happens, right? So, but anyway, we persevered. And this is a plot of midspan displacement range over millions of fatigue cycles. And we can see that displacement increasing early on as we fatigue it, and then sort of plateauing at around, 1.5 million cycles and going out fairly constant, which is a good indicator that we're not accumulating a lot of additional damage, right? When the girder did not fail, the 3 million cycles was not chosen arbitrarily. It was consistent with what AASHTO would define as a fatigue limit for a steel girder with a welded cover plate. So we said, okay, we have a similar detail with our ply drop. Let's use that as the number of cycles we're going to run. And then when we're done testing it, and this was actually happening, if you were here last year, that test was ongoing while you were here. And we continued to gather data for a couple of months after that. And then we loaded it to failure in January of 2024, that same girder that had been fatigued. And this is what we saw. We saw a failure load of 211 kips. Well, what did we see? With the one we didn't fatigue was like 311, right? Or 313. So we had a 33% loss of capacity. Well, I wasn't real happy about that. I actually left for vacation in Florida a couple of days later, and I was really hoping it wouldn't lose any strength. But that's too much to hope for, right? I mean, we stressed this beam very hard for 3 million cycles, and it still retained more than 43% more capacity than an AASHTO strength 1 loading. So it still had a lot of reserve capacity even after those 3 million fatigue cycles. So that was good news, and its failure mode was identical to the unfatigued beam. In other words, we had rupture of the carbon fiber in the bottom flange, shown on the bottom right, looking up at the bottom of the girder. And we also had subsequently crushing of the concrete deck, but that was a secondary failure. The concrete does not crush before the FRP ruptures here. So this overall appears to be good news, but we have to dig a little bit deeper into this, because when we're designing a bridge, we really want to understand what's going to happen under repeated loadings of real magnitude and real frequency. And this is the most detailed slide I have up here. I'll spend a few minutes on it, but it's designed to illustrate the picture. If you look at the picture on the left, that is stress versus number of cycles. Because we tested 2 beams, I was able to derive, using Miner's rule, what the fatigue curve would look like. In terms of steel girders, you think of SN, it's stress range. When we look at composite, we look at total stress sigma. That's the only difference. And the takeaway message there is that, so we can get that carbon up to a little over 100 KSI in its virgin condition, unfatigued. If we apply 10 million cycles, it'll fail at about 25 KSI. Okay, that's what that says. We can carry 10 million cycles of 25 KSI, and that bottom flange will fail. What's interesting is you see the blue line up there, the dashed blue line. That's what the literature tells you it should do. If you have pure unidirectional aerospace grade carbon, it should be carrying about 60% of its ultimate tensile stress for 10 million cycles. And the girder does not, and it does not simply because it is a large vacuum infused composite. It's not just carbon down there, it's glass and carbon. It's much more complex architecture. It's going to have a lot more porosity. It's going to have more defects, and that's what drives fatigue failure. What we need to do now is put that together with real vehicular loading. That's the middle plot. That's weigh in motion data taken from 2015 NCHRP report that underlies the AASHTO fatigue provisions. That tells you, here's the frequency of vehicles, truckloads that will be crossing over that bridge. Girder moment, that's actually the CDF, the cumulative distribution function for vehicular traffic. We combine that with Miner's rule for damage, which is what underlies the development of fatigue provisions for steel and AASHTO, and you end up down at the bottom. About 3,950 trucks per day per lane for 100 years. That's what it would take to cause the failure. So if you have a 100-year design life, about 4,000 trucks per lane per day. To put that in perspective, that's on the order, depending on the fraction of trucks and traffic, that could be as high as 40,000 vehicles per lane per day. In other words, that's a really high traffic volume. In other words, we don't really have to worry about fatigue. You have to be on a very, very high traffic road, tremendous amount of truck traffic, before fatigue is going to become an issue for this. So that takes us up to the present day, really, in terms of our research, what we've completed, what we've done. At this point, as I mentioned, 4 bridges built across 3 states, 2 more are under construction. We've got a rational design methodology. We can cover the basic limit states. We've disseminated the research results pretty widely. Multiple peer-reviewed papers over the last 18, 19 months have been put out. We've given webinars on girder design. We've given in-person short courses at international conferences. So this is what we're doing to try to get this out there and enhance people's understanding of this technology and promote it as well. We are currently working on a design guide. So the AASHTO Committee on Bridges and Structures, the Subcommittee on Special Structures, is very interested in a design guide for the CT girder. I was out there in June at their annual meeting and presented for about an hour the results of our research and the work that we're doing, and that's something they want to move ahead with. So this is very good. That's going to enhance the acceptance of that technology. Ultimately, it will show clearly how the design methodology works, how it's applied. There'll be examples, all the limit states covered. And most importantly, that allows any engineer, DOT, what have you, you've got one of these bridges on your network, you can go in and load rate that bridge. You can assess it for permit loads, things like that. You can compute moment capacity, shear capacity. You don't need specialized tools to do that. It will be very clear how that process is done. The other thing that's ongoing right now is developing a live load continuity joint. And out to date, all these bridges have been simple spans, and we want to move into continuous spans. And that's a not insignificant challenge. It's shown schematically up here as a 2-span bridge. We need some kind of a splice or continuity joint there in the middle so we can transfer live load moment and superimpose dead load moments over the piers. That's going to open up new application spaces for the CT girders, give us more stiffness, more live load capacity. It's something we do all the time with concrete, right? We do it all the time. We add extra rebar on the top of the deck. We have a continuity pour with the concrete. Concrete bears on concrete in compression. Rebar on the deck carries tension. Everything's good. It's tough for composite girders. To the best of my knowledge, it's not been done, but we have things we've been working on, we can build on that will make this work, in particular, ridging the inside surface of that CT girder, pouring concrete in there and transferring stress via shear across that interface, exactly the way we transfer it between the concrete deck and the girder right now. So this is near-term research and deployment. This is actually deployment in parallel with research. A half-scale specimen is in the process of being fabricated right now at AIT. The girder's been infused. We're getting ready to instrument the rebar and get the specimen together and pour the deck. That'll be up here in the lab in a few weeks. And we'll be putting a few 100,000 fatigue cycles on it and then driving it to failure to test that continuity joint. And we're currently designing that detail for the Stillwater Avenue bridges that are under construction right now that some of you probably drove over on your way here. The 3-span bridge and the 2-span bridge are going to incorporate this joint. Although the bridges are being designed, the girders are being sized as if they're simple spans. So we're going to design that detail, we're going to include that detail, but we are not actually relying on it for strength or stiffness in the final structure. And then we're going to be monitoring that structure longer term to ensure it performs well. Now, I want to close with one thing here. I mean, we talked about this morning in the panel. I didn't anticipate going into as much detail there. Some of this is redundant, but it's important to emphasize is that, the Maine DOT has been really important, right? They've helped fund a lot of the research here. Yes, we have a lot of funding from the University Transportation Center, but we need matching money. The DOT has really stepped up, and they've supported multiple deployments, and they're willing to take a chance and go out there and really help find a pilot project site and get these bridges in service. And that's what it takes. And then AIT Bridges, of course, they're the designer of record, the engineer of record. They fabricate these girders. They license the patent. They're the ones that are actually doing the heavy lifting. And they also have to go out there and market this. They've got to spread the word because their business depends on it. They've made a lot of advances in the manufacturing process as well. The girders that they make today are fundamentally the same as the one we made in the lab 7 or 8 years ago, but they can make it a lot more efficiently with combinations of materials that are a lot easier to work with. The net result of this was development to deployment in about 4 years, which is it's a long time. On the other hand, for large scale infrastructure, it's extremely fast. And I have to say that another reason we've been able to do that is we've been working with these two partners for a long time. And we went through a much longer process the first time around with the concrete filled FRP tubes, AKA the bridge in a backpack. Okay, that one took a little longer to get out there, but we did it and we were successful. And that really greased the skids for this one to happen here. So at this point, I'd like to thank you guys, and I appreciate your attention. We've got two more speakers coming up in this session. We'll hold the questions until we're all done.